Hello, I'm David Noel. Welcome to episode 04 of SMB. The topic today is black holes. We hear more and more about black holes these days, but they're still poorly understood even by professional astronomers. There is ample evidence available, but the interpretation of this evidence has been stymied by a basic myth about black holes. This myth is that black holes cannot emit any light or other forms of energy. In reality, they are the source of some of the biggest outputs of energy in the universe. To understand what is happening, we first have to look at events in the lives of ordinary stars, which produce energy by nuclear fusion and can be called fusion stars. Fusion stars are those on the main sequence of the Hertzsprung-Russell diagram, a way of classifying stars by their colours and masses. Let's look at this diagram. The fusion stars are those on the great diagonal band, which ranges from the top left to bottom right on this diagram. They are what we can regard as normal stars. The white dwarfs on the bottom left and the various giants on the top right are not fusion stars. All the stars on the diagram are within our own galaxy, the Milky Way. When you look at the fusion stars, those on the main sequence band, they obey surprisingly strict rules. The mass of a fusion star determines both its colour and its lifetime. The colour of a star is also fixed by the temperature of its surface. Low-mass stars are dull red and have very long lifetimes. The lowest mass for a star to emit visible light at the lower energy red end of the spectrum is about 7.5% of the mass of our Sun. Medium mass stars are orange or yellow and have medium lifetimes, maybe 10 billion years. Their surface temperatures may be upwards or downwards of 5,000 degrees C. Higher mass stars are blue, tending to violet. They have relatively short lifetimes. The very biggest, perhaps a little over 100 times the mass of our Sun, may last only a few million years. Because high mass stars have such short lifetimes, they are less commonly seen in the heavens. People talk about the lifetimes of stars, but it's not always understood what happens when a fusion star reaches the end of its life. The answer to this is it turns into quite a different sort of star, called a vortex star. During the transition process, which may be quite rapid or very slow, the star exists as a transition star. We can refer to this transition as the blow-up phase. How long blow-up takes and the resulting vortex star depends again on the mass of the star. This graphic shows life cycles for stars. A mid-sized fusion star like our Sun may exist for perhaps 10 billion years until it enters blow-up, when it starts to swell enormously into a giant, becoming a transition star. The outer half of a transition star spreads out, gets thinner, and eventually exposes its inner half. If the star is less than about 5 solar masses to start with, the end result is a white dwarf. Fusion stars which are more massive than about 5 solar masses enter a more rapid blow-up phase earlier. The transition star here is a bigger giant, and the end result is either a neutron star or a black hole, depending on the star's original mass. The situation shown in the graphic is well established and understood. However, it's only quite recently that it's become evident that all the end products, that is white dwarfs, neutron stars and black holes, are all what are called vortex stars, differing only in their masses. A quick look back at the Hertzsprung-Russell diagram shows where the non-fusion stars lie. The white dwarfs at the bottom are vortex stars, end products of blow-up. The various giants at the top right are transition stars. They are still in active blow-up, expanding their outer halves into space, eventually to dissipate as a nebula or cloud. Some stunning photos have been taken of the blow-up phase for stars. This picture of the nebula around a star called A.G. Carinae shows the nebula itself about 5 light years across, with a new vortex star left behind in the centre. A deeper, new understanding of star blow-up is currently emerging. A reference web page is given at the end of this episode. So we've seen that one way black holes and other vortex stars are made is through fusion star blow-up. Let's look now at some of the properties of vortex stars. Here is an artist's representation of a vortex star. It's a useful picture to help the mind grasp the concept, not a direct representation. Vortex stars are very dense, rapidly rotating bodies of high mass. They emit tight beams of energy, and sometimes particles, along their axes of rotation. Their properties obey the law of physics, but they are extreme cases. Unlike most conventional objects, the higher their mass, the smaller and denser they are. Their emission beams put out huge amounts of energy in very narrow beams. The more massive the vortex star, the higher the energy of their outputs, which can range conventional visible light up through X-rays, gamma rays and beyond into particles such as protons. Their emission beams are very tightly collimated, that is, formed into very narrow beams with negligible spread, rather like laser beams. These collimated beams have 2 important consequences. First, because they don't spread, they are only visible easily when looking down one of their axes. There are secondary manifestations, such as the galactic jets and stellar jets, which are sometimes photographed in the heavens, but these come from the collimated beams happening to strike bits of intervening matter. The second thing is the collimated beams can travel a very long way because they lose very little energy along the ray. Most of the very distant objects we know about, 10 billion light years or more away, are the axial beams from AGNs or supermassive black holes lying at the centres of galaxies. We only see those which happen to have their axial beams pointing directly at us. These galaxies are flat on to us. So we know that black holes and other vortex stars put out huge amounts of light and other forms of energy. What then is the reason for the story that light cannot escape from them? The cause of this is based on the concept of black holes, which is very different to the real black holes we see in the universe. It's all based on some calculations done by Karl Schwarzschild back around 1916. In his calculations, Schwarzschild showed that in an object of sufficient mass, a so-called non-rotating black hole, gravity will be so great that nothing could pass out beyond a given distance. This distance is called the Schwarzschild radius, or in popular speech, the event horizon. There's nothing wrong with Schwarzschild's calculations, but they apply to an object which does not exist. It's like doing a very accurate calculation of how much food your dragon would eat in a month. A calculation like this is irrelevant if your dragon is imaginary. The thing is, Schwarzschild's calculation applies to a non-rotating black hole. There is no real evidence of a non-rotating black hole existing in the real universe, and there are good theoretical reasons why they can't exist. So event horizons and all the black hole stories you hear about are just a diversion from the truth. In the real world, lower mass black holes form after fusion stars split apart in the blowout process, and higher mass black holes, such as the AGNs which lie at the centre of all galaxies, formed by accumulation of smaller black holes, stars, and other matter and energy within their gravitational reach. They're called vortex stars because, like all vortexes, they try to drag in stuff from their surroundings. There is a lot more to this subject, some of which will feature in later episodes of SMB. Following is a link to a reference article on the web which gives more detail and links on the current topic. And finally, some links to other sources available to you, both episodes on our YouTube channel and a website including articles which quote established and referenced data. Have a look. So it's goodbye from me, David Noel. I hope you like these efforts to make the universe a bit simpler to understand.